All right, welcome back to our video lecture series on chapter 6.3, looking at inferences for a difference of two proportions. All right, in the last video, we went through example 2, how detrimental are metal tags to penguins. We looked at a 10-year survival rate. There 20% of 162 metal tag penguins survived, whereas a much higher 36% of 189 electronic tag penguins survived. So we went through the formula. We checked to make sure that we had at least 10 successes and failures in each group, which we do. So we can use normal distribution. For 90% confidence, Z star is 1.645. And then we threw all our information into the formula for difference of proportions to get 90% confident that electronic tag penguins survive 8.3 to 23.7% more than metal tagged penguins. Okay, so on the slides, I forgot I wrote this up on the slides, and kind of make sure here we have at least 10 successes and failures. All right, the only thing done differently here is I made group 1. This is the metal tag group. C star is the same. These two got switched, but we're adding them together, so it doesn't matter what order you add the two numbers together. But we do get a negative statistic since I switched the two groups from the last video. And we got minus 0.237 to minus 0.083. So that is a different confidence interval. From over here, I made sure I had a positive statistic. I think it's maybe a little trickier to interpret negative numbers, but the interpretation is the same. We're 90% confident that the survival rate is between 9, that should be 0.8, oops, excuse me, 8 and 23.7 lower for metal tagged penguins as opposed to electronically tagged. So here I have lower for metal tagged as my interpretation, whereas here I have electronic tag has a higher survival rate. So both these interpretations are saying the same thing, and in practice you can actually subtract either way. All right. Here I'm looking at going back to chapter 3. You can do a bootstrap dot plot for just difference of two proportions, and if you put your information in, get a whole bunch of samples. You see here, again, you won't get the exact same confidence interval, but it should be pretty close to what we just did. And actually, before I go to the next example, I want to show you a slightly different way to get this confidence interval using GeoGebra. So you can use GeoGebra to calculate confidence intervals if you prefer. So I'm giving you options on this. The formulas work. I've had students that prefer the formulas, and then I have students that don't like the big old messy square root formula, and that's fine as long as you can use the software appropriately and interpret your answer appropriately. I'm very okay with using GeoGebra. So if you want to do that, Google GeoGebra, and you should end up on the top spot should be here. If you click on GeoGebra, we did this a couple of days ago. We want to click on that probability tab. Make sure, up here, click on statistics. We want to look at statistics, and here you have this drop-down menu. So I've got z-test of a mean, t-test of a mean. So these are all hypothesis tests. So we're not going to use that because I want to do a confidence interval. And confidence intervals are all going to be estimations. So z-estimate, difference of proportions. So if I click on that, I got z-estimate difference of proportions. Confidence level, we're doing a 90% confidence level, so 0.90. And now I need successes and total sample size. So sample 1, and I don't know why GeoGebra the 1 doesn't appear, versus sample 2. So I'm going to go back here and say, I'm going to use, so I get the same numbers as we did on last video. I'm going to let sample 1 be the 64 successes. So 68.04 successes out of 189. So I'm going to do 68.04. Go down here, change that to 189. And for sample 2, I'm going to make sample 2 the metal group. And here we have 33.4 successes out of 167. Yeah, 167 metal. So I'm going to enter 33.4 successes out of 167. And here, sometimes it's a little clunky software. You might need to click enter more than once. And here you want to read down below. See, here we have the 2 samples. There's standard error, 0.0467. There's our standard error right there, 0.04666, which is the same when you round it to that. 3 decimals. And then we've got lower limit, upper limit, 0.0833 and 0.2367, which is exactly what we got using the formulas. And it also gives that margin of error, 0.076, 0.0767, so the margin of error. So you're definitely allowed to use GeoGebra to help calculate confidence intervals. And later on, I'll show you how to use this to get p-values for hypothesis testing. All right, excellent. All right, I want to look at, this was a English or British game. Kind of like our Who Wants to Be a Millionaire, very popular name called Golden Balls. I'm actually going to show this YouTube clip in our next class. If you want to watch it beforehand, that's fine. You can just click on this link. But it's like about a 4 or 5 minute clip. I think it's fairly entertaining. But we'll go over that I'm going to show that in next class. But if both choose split, they split the jackpot. If both choose steal, they both get nothing. These are 2 players playing against each other. If one steals and one splits, the stealer gets everything. This is a variation on either the liar's paradox. Excuse me, not the liar's paradox. This is a variation of the prisoner's dilemma. I've studied that in a philosophy class or game theory. The idea is, what would you do? Would you split? And if the other person picks split, you split your money, or would you steal and help you get the whole thing or nothing? Maybe we'll do a vote on this next class when we meet. But this study was done, linked down here, was looking at a whole bunch of these game shows. And here we have a bunch of, to a table where a big group, 574, excuse me. So if we take half of that, there's 287 games played because there's 2 players. And they looked only at male and female, when a male was opposed to a female. And here we have our split setup. 140 males selected split as opposed to 163. And then 129 males said split out of 269. And then here we have our total columns. So the question posed is, are males or females more cooperative? Again, we're going to assume cooperative means to split. So let's designate some population parameters. Let P sub n be the proportion of males who split. So not these, this is just a sample. I'm going to call this P hat in a moment. And PF would be the proportion of females who split, because this is only a sample of games, and then the show could keep going, or be revived, or come to the United States, and get a much bigger sample size. All right, so the first thing we want to do is calculate the sample statistic, P hat M minus P hat F. So if we set it up this way, P hat M is going to be the proportion of males who split, so that's 140 over 269. And then we're going to subtract the proportion of females who split, which is 163 over 305. So 140 over 269 minus 163 over 305. Subtract those 2, and I get minus 0.015. And again, you have the option here. I could have switched those up and make this a positive number, or keep it as is. So this negative means that females have a slightly higher, 4% higher proportion of splitting than males. But that's pretty close. There's not too big of a difference there. So for hypothesis testing, we want the distribution of the sample proportions assuming the null hypothesis is true. So our null will be that P1 equals P2. Or in the last example, I'll write this as PM equals PW. Standard error formula is still the same, but we don't have a P1 or P2. So the question becomes, well, what do we use for P1 and P2? For confidence intervals, we use P hat 1 and P hat 2. And sometimes you do that here, but it's a little bit more complicated. We assume the proportions are the same between the two groups, and we want to use one proportion, that's our best guess for what they would be, if they were equal. Again, this is the null hypothesis, we're assuming they're equal. So we're going to combine both groups into one big group and use the overall proportion. We're going to call this the pooled proportion P hat. The pooled proportion will always be somewhere between P hat 1 and P hat 2. So here we have our information. The pooled proportion is the overall proportion who split. So who split, we've got 303 total split out of 574. So we're going to assume that P hat is 0.528. Again, this is called pooled proportion. We're combining both groups. And the reason why we're doing this is for the null hypothesis, we're assuming those two proportions are equal. So I want to use one proportion in the standard error formula. And here we have our statistic minus the null over standard error, our standard setup for hypothesis testing. And here are setting this formula. The statistic is P hat 1 minus P hat 2. In this class, we're always going to assume the null is 0, assume no difference of proportions. And then we're going to take the square root of P hat times 1 minus P hat over the first sample size plus P hat times 1 minus P hat over the second sample size. And this is that pooled proportion we calculated on the last slide. And we also need the requirement that the number of successes here, n times P hat is greater than 10, and n times 1 minus P hat is greater than 10 for both sample sizes. Then the p-value can be computed as the area using normal distribution. So this is the assumption to be able to use the normal distribution. All right, so based on the data, can we conclude whether males or females are significantly more cooperative when playing golden balls? All right, here, the null hypothesis, we're going to assume the two population proportions are equal, and we're going to say the alternative is not equal. So don't forget, when we calculate p-value, this means we're going to double the area of the tail. Counts are greater than 10 in each category. Again, we could calculate these numbers, but if I just look at these values, these are all much, much greater than 10. So as long as all 4 categories are 10 or more, we could use Z. Our P hat is the 303 over 574 to be the 0.528. All right, again, it's a messy formula, but Z is P hat 1 minus P hat 2 over the standard error formula. P hat 1 minus P hat 2 is 0.520 minus 0.534. The numerator we already calculated to be minus 0.017. And this giant messy square root formula. Notice here, we're using that P hat pooled proportion for P. But the difference is we're dividing by 2 different sample sizes. Where did that 269 come from? That came from the total males, and the 305 comes from total females. And we got the statistic to be minus 0.033. All right, here on the side, we got the p-value is equal to 2 times 0.371. Our p-value is 0.742. And on the next video, we're going to complete this, write a conclusion. I'm going to show how to get this p-value on Stacky. And then we're going to go through this process again using GeoGebra.